Good afternoon, everyone. Okay. Am I audible to the one sitting in backside? Okay, cool. So I know that the timeline has been shifted a bit and you might be waiting for the workshop to end so that you can go and get your lunch. But just hold on for the next 20 minutes. The time you spend here would be worth if you are working with LLM inference or AI inference. So the topic that I would be speaking today is optimizing LLM inference on resource constrained hardware. So if you look at the timetable or the contribution I have posted in the canonical page, you might see that there is a small correction I have made with the subtitle of my talk. Initially, I thought about telling you about a particular framework, how you can use that framework for LLM inference. But later I had a thought because in A particularly, you shouldn't learn about frameworks or tools because tools can come at any time and later you get changed at the core, what you should learn is the fundamental thing that keeps running. Maybe there could be some math behind it. There could be some optimization algorithm or any sort of thing used there. So my whole talk is based on the some of the theory or theoretical aspect. Usually I speak a lot about the hands-on side or the engineering side, but here I'd be focusing more on the theory. But that would be much more beneficial for you as well. So that's why we are doing that. And since it's being a bit theory, I'll try to make it as much as engaging and it's you who should make me energetic as well. So I've been traveling from Kochi and I landed today morning and I am also a tired bit. So it's your faces that should make me energetic throughout the workshop. Done? Be some more energetic. We'll have lunch. Okay, cool. So myself, I'm Abdul Hakkeem and I'm doing my, I'm a, I'll go to that slide. So I'm particularly working on inference optimization. So why I'm working on inference optimization? Because if you look at LLMs or what all major or foundational models, 10% of the top companies would be working on building foundational models. And the rest of the 90% are doing what? Inference using that. So you have to make the inference pipeline much more efficient. It should be a really optimal solution. And as related, I'm also working with MLOps as well. And on a side note, I'm working as an research and development intern at a fintech startup in Kochi. And I'm exploring on how you could integrate AI agents or LLMs into fintech work solutions, especially for B2B sector. And I still do my master's. I'm currently doing my master's at Cochin University of Science and Technology. It's at Kerala. And I published two research papers in machine learning operations, one at a conference in USA and another at Bangalore at 2-3 months ago. And I'm also an active open source contributor. I have contributed to the HuggingFace library. There's a small agents library which is used for running AI agents, and I have contributed to that library. Apart from that, I contributed to the YOLO repository and also in Physical. In Physical is a secret management tool which is open source. And uh, re- with this ST thing, I run community events as well, like these people do. I've been part of various communities in Kochi, and primarily I've been working with the AWS user group. We have been running a cloud community day called AWS Community Day every month. So not every month, every year. So this is about me, and let's get started into the core of what we are solving. Okay. So before we jump directly into LLM inference, let's set the context for the audience so that we have a good storyline. And in 2023, everyone saw the what introduction of ChatGPT, right? So that came up from a paper which was introduced by Google in 2017, and ChatGPT or the OpenAI has eventually made it to a product that made everyone wonder. So how many of you got wondered with why using ChatGPT in 2022? Even I got wondered looking at the power of how text generation works. And eventually, when we started working with or started using ChatGPT for various tasks like completing an email, summarizing various documents, or even writing code, we saw how our productivity or how our workflow has been increased. So, inspired from that, startups and enterprises have been trying to integrate LLM powered features into the products that they already own. And soon products have been or the entire the technology or the entire economy has been changed with LLM. What all tool you see, it's powered by LLM now, right? So, and in 2025, you could see that every product is now an AI copilot. Everyone has a RAG agent. You know what RAG means? Okay, so it's retrieval augmented generation, and they are also use LLMs. And you have chatbots which are very efficient than from once been in the past. And obviously now everyone wants AI agents, which is the hot topic now. So for all these things, what you need an LLM, right? So primarily, even me also for rapid prototyping, I use APIs provided by OpenAI or Gemma, or not Gemma, by Gemini, Cloudy, or those kinds of provider. But what's the problem when we use these kinds of API? Yeah, obviously we have to pay for that. We have some kind of free tier still, but the fundamental problem is that we don't have a control over some extent. Uh, they are mostly biased towards what western side or the those data set. We don't have something more specific to our index set, and we don't have most of the thing would be for generalized purpose. Maybe if I want something for fintech or what all sort purpose, you can't use a cloud sourced API to fine tune it for yourself. There are some providers who support fine tuning, but it's at higher costly. And also the most dangerous problem is that the data is leaving out of your laptop, either your organization. So we don't want to do that. We are fans of open source and we wanted to do it at the open source thing, right? So at this moment, I need to give a shout out to these companies or research labs. So they have been pushing the open source AI community or the open source LLM space. So what Llama, Mistral, Quen, IBM, DeepMind, DeepSeek, they have been regularly improving their models. They have been pushing it regularly. If you look at Quen has been releasing their vision and LLM models regularly basis. And IBM has been recently developed and released their Granite model. Everyone, even DeepMind is solving tons of problems with LLMs and other kinds of models. So now you have an open source model, you can solve many kinds of problems that we have been talking in the previous slide. The data problem, the flexibility, you can fine tune now. And after fine tune, what you will do? You have to deploy, right? Either you could run it on your laptop for your personal purpose, or maybe on a small resource constrained hardware like a small GPU instance you can run. But there comes the actual problem. Even I can tell that running LLMs or it's a one time setup. You need to set up the infra for one time. You have a lot of cost control. You can do everything at your space, at your control. But here is the main problem. How many of you have faced this problem out of memory? Okay, pretty good. So everyone have been trying with LLM, and this is the actual problem. LLM has been very thirsty at VRAM or memory, and luckily our laptop didn't have that much memory that LLMs need. So how we can solve this problem? Okay, so these are the fundamental problem when you run LLM at your own. Obviously, the models are too large and you get very slow response. When you use ChatGPT and when you run an LLM at your own laptop, you understand, right? How difficult it's to get that the speed or that the tokens. So and also you are facing difficulty for one prompt at a time. So then how can you scale? So scaling is also a difficult problem, and obviously the main fundamental bottleneck is memory. So how we can solve these problems? Okay. So if you look at this is the VRAM consumption of popular LLM models when the number of parameters is increasing. See, you can see from a 6 billion model to 34 billion model how the VRAM size is increasing. So you get the problem, right? You have the open source model, but it consumes a lot of VRAM. So how we could solve this problem smartly? And next time when you pick a model, you can literally use this equation to compute how much more the memory that model might use. So when you the P represents the parameter, the B represents the bytes per parameter, and Q is the quantization factor, and you get the memory in bytes. And eventually you can convert it to gigabytes, and you can identify how much VRAM that particular model needs to run. And before you get into OOM or the out of memory error, you can use this and find whether you have the actual capacity to run or not. Okay. So, okay. And now we are talking about how you deploy LLMs, right? So, we, eh, how we evaluate every LLM system or how system, we have some kind of benchmarks, like, and we will be particularly using these benchmark to evaluate how LLMs can be evaluated or how its performance is. The first one is time to first token. So it's, so how many of you know that LLMs are auto-regressive model? Okay. So what does autoregressive mean? I'll tell that. So autoregressive means that LLM generates text one by one at a time. So let's say I give an input I saw to an LLM and ask the LLM to complete the sentence. What LLM does is it completes based on some calculation internally. So I saw A, and then it re-gives that input into the LLM again. I saw a what? Cat. On. So each word is generated one by one at a time. So that's how we use time to first token. When we give a request to the LLM and how much time it takes to compute the first token. So that's TTFT. And next is the total latency, E2EL. That measures from the first token to the last token. So we gave the request and it's the time at which we receive the last token from the LLM. So it measures the total latency. And the next one is the inter token latency. So the tokens are generated one by one at a time. So it measures how much time is there between each token. So and next obviously we have throughput. Throughput you might be knowing. So how much request you can consume run parallel, or how much request you can be accommodated by that LLM. So these are the 4 parameters that you can use when you run LLMs, if at your laptop or even on a on-prem, or even at your private cloud as well. So you can literally use these parameters. So what are we really optimizing for? So what we want for the users, we don't want the user to wait for too much time, right? So we want faster response, which means that we need to reduce the latency, and we want to we are not doing this for one user, for the number of users that we have. So for what we need to increase the throughput so that we can process the request as much as we can. So we are trying to reduce the latency and also increasing the throughput. Okay, cool. So before we get into optimization thing, I would like to look into this thing. So LLM inference happens at 2 stages. One is the pre-fill stage and another is decode stage. So in pre-fill stage, what happens is that when you give an input to the LLM, which is in the form of a prompt, it computes the KV cache from that particular prompt. How many of you know about KV cache here? Okay, no worries, no worries. So it computes the what? KV cache. Just keep that word in your mind. I'll come to that later. And next is the decode process. The decode process is what I have told about the token by token generation. So this KV cache is used to construct a context from the prompt that we give to the LLM. So using that prompt, the context, what the LLM can generate new text or new tokens based on that context. So it's 2 stages: pre-fill stage and decode stage. Okay. Okay. So okay. How many of you have heard about attention mechanism? Okay, a few people. No worries. So as every neural network, what is an LLM? LLM is another neural network. It's a large language model, but we are making it by stacking different neural networks layer by layer together. And what gives this large language model the ultimate power is that it has some special type of layers called attention mechanism. I'm not going much depth into that, but you should learn what is attention and how this works. Then only you get the eventual crux of running an LLM. So what attention helps here is that there are 2 types of attention: self-attention and multi-head attention. And when you run attention mechanism, you can identify different patterns in the input prompt or in the data. You can identify where you want to give more prominence to the prompt. Let's say if user asks something and you want to identify what the user means. So attention mechanism eventually gives you the scores for the particular area or particular token you want to attend more. So that's what attention mechanism in simple terms. So in attention mechanism, basically what we do is we have 3 metrics. It's called QKV metrics. You have a query metrics, you have a key metrics, and you have a value metrics. And you will be computing the context. You remember the context vector that I said in the previous slide? Okay. So we would be computing the context using the by computing what the query vector into the key vector, and then we perform the value vector into the attention that we performed using in the previous step. So what happens here is when you have a prompt and when you are generating the model each time. So what we can do is we can compute the KV cache for the initial prompt at first time, and we can store it as cache. Why we are doing is that next time when we generate a token, so this would be done at the pre-fill stage. What? Computing the KV cache and storing it as computing the KV metrics and storing it as cache. And in the next decode phase, we would be generating each token. So eventually that tokens would be added into the key and value metrics, and we would compute the context vector again for the new tokens as well. So what we can do is we already have the context of the previous initial prompt. We don't have to recompute that again. You got my point? So what we do is we add new tokens to the key and value and only compute for the new tokens that we have added. In that way, we are not recomputing that. So why we are not recomputing is that LLM inference is mostly a memory bound problem. It's not a computation bound. So when you use the KV cache, you save a lot of memory and you save a lot of computation. You don't want to do things iteratively. So that's the power of KV cache. And this KV cache brings another set of challenges for the LLM inference. We'll talk about that in later. Now, I hope you have a basic idea of how autoregressive models work, what is KV cache, what is attention mechanism. Yes? Okay. So these are the practical bottlenecks inside LLM inference. So I told you about the transformer architecture. It's that powers the LLMs that you see today. So the vanilla transformer architecture that was introduced in the research paper, it's not an ideal one for production purpose. So that's the whole the problem that causes a lot of issues. And the next problem is that, as I told you, LLM inference is mostly a compute bound, memory bound problem rather than a compute bound problem. So if you're not managing the memory enough, you get these kinds of problem out of memory. So, and we have talked about KV cache in the previous slide. And what we want to do, we have, so the frameworks that were in the traditional LLM inference did an inefficient GPU memory management, especially with KV cache. So that was a fundamental problem. And we'll try to see how we can solve that. And also the GPU utilization is not completely utilized in heavy workloads as well. And the token generation is inherently sequential. I told you, right, how autoregressive models are, one token at a time. So these are the practical problems that you can solve in LLM inference so that you could eventually increase the performance of the system. So I have specifically noted this system in such a way that you don't have to adjust the model parameters and you don't have to do the retraining again. This can be done using some kind of engineering techniques and some kind of algorithm optimization. So that's why I specifically use this, because as engineers, we can do this easily, but we can't do the other way. We can't take a huge model. We can't retrain it from scratch again to make it run only on my laptop or for a specific purpose. So the whole purpose is to do things at a simple scale. Okay. So these are some of the techniques that we use to optimize the LLM inference. So the first thing is page retention. The next one is continuous patching. The third one is speculative decoding. The fourth one is prefix chunking, and the fifth one is quantization. And I'm pretty sure that you have heard about quantization before. Note the 4 points back. Have anyone heard about this back? Okay, one. Cool. So we'll come tell about page retention. So what page retention is? I talked about the attention mechanism, right? Okay. So when if we go back to the previous slide, so this is the equation that we use for computing attention. You can see that we use k and value for computing attention. So where we have stored it, it is stored in the form of cache, right? But what if I am storing this KV cache in contiguous memory? So so the traditional frameworks, these K and V values were stored in what? Contiguous memory. So the problem with the K and V was the user or the engineer, I don't know what would be the eventual length of the user prompt or what would be the output length, because I can't predict what it's common, right? So what they did was they for every LLM it has a max token length, right? So they allocated the entire max token length for each request. So what this leads to? Yeah, fragmentation. It leads to both external fragmentation and internal fragmentation. So that was a fundamental problem with inefficient memory management. So what page retention does was, okay. So page retention was a specialized algorithm which was used to compute attention from the KV cache, not from the contiguous memory. It was distributed in what? Non-contiguous memories. So the non-contiguous memory allocation was inspired from the very on operating systems, virtual memory, and the paging techniques that we use. So we tried to divide the KV cache into number of blocks and pages, and then recompute the attention using the page retention algorithm. So page retention is nothing. It's the tweaked version of the attention algorithm, but for working with non-contiguous memory allocation. So allocating what the KV cache in non-contiguous manner. What we have much more flexibility in handling what different requests. So uh, i- instead of allocating the whole memory for a single request, I can now allocate much more requests since I have much more what memory spaces left. So this is something about page retention. And the next thing is iteration level scheduling. So it is also known by the name continuous batching. So if you look at Google or any other paper, you can see that maybe it could be dynamic batching or continuous batching or iteration level schedule. So this was another problem with LLM inference with traditional system. So when you use any framework for LLM inference, there had two components. One was a scheduler and another was the LLM inference engine. So when you send a request to that particular engine, it the request comes at scheduler, like the web server that used to collect all the requests, and eventually it sends the request to the corresponding port or the corresponding endpoint. So what the scheduler does in static batching was they had, let's say, in a batch we can accommodate two requests, and we took two requests into the the particular batch, and we have been starting to try generate the request or the generate tokens one by one. And suppose for the first request, within one token we have ended that particular request, and for the second request we are still generating tokens. But with traditional or static batching, the problem with that was, even if the first request is still completed, it has to wait for the second request to complete. Then only the user will receive the response back. So the user has to wait for longer time. At the same time, if another request is still in the queue with the scheduler, he also has to wait or has to starve till the second request or the longer request has to complete. So this was one problem. And how it's all using continuous batching or iteration level scheduling is that it tries to generate what tokens in each schedule. Let's say at the initial phase we had at the initial phase we had four requests, and we were generating tokens one by at a time. So the yellow color represents the KV cache or the tokens which were earlier in the prompt, and the blue ones are the tokens what we are generating. Okay, so you see that at each level, for each request we are generating new token. And going to a second slide, and you can see that at T5, the fifth step, the third request has entered, which means that okay, it has correctly generated all the output for the user. And now what it did, it accommodated the next request, S5, into that particular row. And you can similarly see that in the entire pattern. In earlier, what happened was, if everything ended at this pace, uh, it has to wait for S4 to finish. Then only it could accommodate the next request. I hope you got the point, right? So these are small engineering tweaks that are using, but you could really increase the throughput and you could really reduce the latency for the user as well. It's not thread, it's the number of requests in the batch, in that particular batch. Let's say if 4 is the batch size and 4 requests are being currently processed by that LLM. Yeah. Okay. So the next thing is speculative decoding. So I am repointing that LLMs are autoregressive model and it has to generate one text one by one at a time. So let me take an example. I saw. This is the prompt that I give to an LLM, and the LLM has to complete that statement. So what it does, I saw. The next word it generate might be A. I saw A. And then it has to feed that again into the LLM. So I saw a cat. Again, it has to feed that into the LLM. I saw a cat on. Then next, maybe it could be Bangalore on what, a Saturday morning. So it has to generate text one by one at a time. And you have seen the LLMs are pretty large, and generating each token one by at a time, it's really hard. So how we can solve that problem smartly? So it's called speculative decoding, and it came out of a research paper as well. So what speculative decoding does is that you have two models here. So one would be a draft model and another would be a target model. So the target model is the one that we are aiming to use for generating the text. But it's very hard that it takes a lot of time to generate the tokens one by at a time. So what we use? We use a draft model which will generate the text with the input prompt that we give. So suppose I walked with this the initial prompt that I gave, and the draft model generated. I walked with my cat's yellow. And what it does next? it gives that generated text into the target model once again. So in single pass, the target model can verify which all are correct according to his rules. So you see, the target model has accepted my and rejected cats and yellow. And what it does next, it generates the corresponding words for the rejected words. And so, and now you see, I walked with my friends who. So this would be again given back to a draft model, which would generate next set of tokens. And again, it would be given to a target model. So in this how we are, in this way, we could make the text generation much more faster. It's like the kind of a teacher-student model where student writes a lot of thing and the teacher approves whether it's correct or not. So the teacher can eventually save his her time a lot. So this is about speculative decoding. And the next thing is prefix caching. So this is something very, I mean, as everyone, you might be knowing about caching. We have talked about KV cache and the type of cache. So in cache, what we do, instead of recomputing again, we use something which was computed once, right? So, so how many of you have tried building LLM wrappers, chatbots, AI agents here? Okay. So you might have used a prompt, a system instruction to make that thing work, right? So what's common with that system instruction? For each request, the system instruction or the prompt is particularly common, right? Only the things with the particular user will change. So what we can do here? So do we need to compute the KV cache, the attention, all these things for that prompt again? No. So what you can do? Suppose this is my system instruction for a chatbot. You are a helpful AI writer. Please write in a professional manner. This is common. And the next thing that each user gives is particular to his or her requirement. So that thing might change. I can compute the KV cache and store it as a cache, right? And then attach it to the particular input that user gives. So this is called what? Prefix caching. You identify at certain level what is the prefix that doesn't change all the time, and you cache the KV cache or related fields, and you store it in cache, and you reuse that for systems. So this is particularly useful for systems that are AI agents, RAG pipeline, or chat, or anything that has a common prompt or a common instruction. So throughout all this, you might, yeah, I'll wrap it soon. So with all these things, you might have understood with a small tweak of engineering how much we could improve the latency, how much we could improve the throughput of that particular system. And we'll go to the last topic as well. So quantization. So I hope that some of you might have heard about quantization. So in quantization, what we do here is when you train a model, the weights would be particularly in FP32, which is a single precision. So uh, again, going back to the equation that I have used here. So here we had a Q parameter, which is the bit precision used for quantization. So if from this equation, what you can identify, if you increase the quantization, what will happen? The memory requirement will be increase. Yeah. So that is if I use 32-bit quantization, it would be 1. And if I use 16, what happened? Not 64, 32 by 16, 2. And you cut the memory by 2, right? Okay. So what we are doing here, 32 is the full precision, and by doing it 16, we are doing the precision to half, which is FP16, floating point 16. Y- Got got it? Any confusion? Yeah. So okay. So these are the various quantization that you can see from FP32. You can go for int 8, and then you can go for int 4. And so quantization is usually performed once after you do the training. It's called post-training quantization. But when you apply quantization, you have to expect there could be some trade-off between the accuracy or the quality of that model. So there's another type of quantization. It's called QAT, quantization aware training. When you train models also, you can apply quantization. So if there are people who are trying to build foundational models, you can try using QAT. So that you don't have to do quantization after you train. So you don't have to end up with losing your accuracy or the quality of the model. So we are I'm going to the last part of the session, and I'm introducing a framework here called, it's called VLLM. How many of you heard about VLLM? Okay. So I've told about a couple of engineering techniques. Do you want to implement it your own, or you want a framework that handles all this? Yeah, so that's VLLM. So, and one more thing, VLLM was that group who introduced the page retention algorithm as well. So they eventually made a research paper, and then only the VLLM project came out. It's open source as well. So you could go into GitHub and you could check out about VLLM. So what's the features of VLLM? You have the best SOTA, state of the art performing throughput for a current LLM system, and it also provides both type of streaming, whether you could do it as a streaming output or a direct text based output, and it has an OpenAI compatible API server as well. So if you have integrated OpenAI at some time and you don't want to make the code base change, you can still use VLLM to serve your own model and use the same code base itself. And it has integration with almost all the models in Hugging Face. If that model doesn't work, you can raise an issue in VLLM repo. The team is very supportive. They will add support for that project, and it supports various decoding algorithms as well. So it's a good framework where you could use for LLM serving. And these are a few examples of how you could use VLLM. Using this single command, VLLM server, and the particular model from Hugging Face, you can spin up that server. So that server would be running in parallel, running in your system. And this is the code we use to connect with OpenAI. And you can use the same code to connect with the model that we have spinned up. So that's the whole power of VLLM. So this documentation is available within the VLLM page. So if you go and check out, you can host it up simply. And it's another type. So the thing I have mentioned earlier is online serving, where you serve it for the users. If you have a script or a notebook where you want to use VLLM, you can import VLLM from their package itself. So this is called offline serving. And we have mentioned about speculative decoding, right? All the other techniques that I've mentioned is by default integrated in VLLM when you use online serving. And if you want to use speculative decoding, you can add that parameter speculative config, and you can mention which model you want to use as the draft model. So there you can see that we are using a 6.7 billion parameter model as the target model, and we use a 125 million parameter model as a draft model. So you identify the trade-off, right? A 125 million model would be using for generating the text, and 6.7 billion model would be used in for what? Evaluating that model. So in that way, you could make the text generation process much more faster. Yeah. Yeah, it's just a moment. And we are done. And this is my socials. If you want connected, you can send request on that. So yeah, thank you.